everyone and welcome to Mechelen 360. All right, so in this video I want to solve a question, a simple question to illustrate the Euler load with you. All right, so basically in this problem we have been given a hollow mouth steel tube which is 6 meters long. So the length is 6,000 millimeters, and then internal diameter, so let's call that small d, 4 centimeters, which is like 40 millimeters, and then 5 millimeter thickness. Okay, so that is like um the the thickness, and that's 5 millimeters. All right, and then use as a strut with both end hinged. Now I want you to look at it very carefully. Both ends hinged. All right, because if you don't have idea about how the hinge is, the end condition is, you wouldn't know which Euler load to apply. Okay, so please pay attention to that. And then he says find the crippling load, or the collapsing load, and then the safe load, taking factor of safety as what? 3. Okay, so our factor of safety is 3, and we are to take E as 2 times 10 to the power 5 Newton per millimeter squared. So this question is pretty much simple. This one is some sort of hollow, so it means it has got external and internal diameter. So this is how you go about it. You have a cylindrical, but you have a cross-sectional area. So let's say this is the smaller diameter, and the one outside here is the bigger diameter. Okay, all right, so that space between the small and the big is what we call the thickness. All right, so it means that from here to here is thickness, and then this is also thickness. Now you observe that if we trace this here, so that's going to be the length, and then this is going to be for the smaller diameter. Carefully, you can see that the bigger diameter is going to be the thickness plus the smaller diameter plus the thickness. That's to say, the entire diameter in this direction will be the small thickness over here plus the small diameter plus the other small thickness over there. All right, so yeah, we can say that the diameter, which is the external diameter, is going to be 2 times the thickness plus the small diameter, and that is 2 times 5 plus 40. So basically we can do this, right? 2 times 5 is 10, and then 10 plus 40 is 50 millimeters, right? So essentially the bigger diameter is actually 50 millimeters. Now he said both end hinge. For Euler load, if both end is hinged, the Euler load is pi squared EI divided by LE squared, where LE is effective length, but then if I have both ends hinged, then the effective length is nothing but the length itself. But then the I, which is the area moment of inertia, is going to be given by I, which is what? Pi over 64 big D to the power 4 minus small d to the power 4. So pay attention here. If it was just a single diameter, that one, it will be pi d4 over 64. But then this one, it is having inner and outer diameter. Okay, so that's why we are doing this. So if you put everything inside, it's going to be pi over 64 into 50 to the power 4 minus 40 to the power 4. So basically, that's what we are going to get for the okay. So let's pick our calculators. I think that is it. Let's pick our calculators and then compute the area moment of inertia. So that's going to be pi. So pi divided by 64 and then multiplied by 50 to the power 4 and then minus 40 to the power 4, and then that gives us 181132. So I is 181132.45 millimeters to the power 4. So that is sort of the area moment of inertia. Now we can go ahead and then find the Euler load. So the Euler load becomes pi squared multiplied by 2 times 10 to the power 5, and then I, which is what 181132.45 all divided by the length squared. The length was given as 6 meters, which is like 6,000 millimeters. So squared, and that gives us the Euler load. So it's going to be pi multiplied by 2 times 10 to the power 5, and then multiplied by 181132.45 divided by 6,000 squared, and then that is it. So basically the Euler load is around 3.16 kilonewtons. Okay, so 3.16 kilonewtons. So that's basically the Euler load. Okay, so now that you have the Euler load, okay, so now that you have the Euler load, let's try and calculate the load that we want. Okay, let's calculate the load that we want. Oh, sorry, please. I'm really sorry. I did not square the pi. I think someone will be asking. So please, I have done it. Thank you. So basically, the answer is not supposed to be 3.16. I have to square the pi. Okay, the formula is pi squared. Okay, if you do that, this is the actual answer: 9931.697. So let's say 9931.7. So 9931.7 newtons, or so approximately we have 9.93 kilonewtons. So that's basically the Euler load. Okay, but we've been given a factor of safety, and then we've been asked to calculate the safe load. So now when we say the factor of safety is like where are we going? I mean, how safe are we? So if someone says, give me a safe factor of say 3, then from the question said the factor of safety is 3, meaning that at the end of the day, the actual design load that I'm going to use is going to be 3 times the basic load. Okay, So think about this way. If this 9.93 will fail it, then we want to design 3 times that of this. So in other words, the safe load that we are going to get will be divided. Okay, so in other words, all what we are trying to say is that to get the safe load, then it's going to be the crippling load divided by the factor of safety. That's all. So it's going to be so the safe load is going to be the crippling load, which we know that this is what will cause the failure. Then we divide it by the 3, so that whatever we are going to get, it means that if we use this design, then basically it means we have used a factor of safety of 3. That's basically what it means. So 9.93 divided by 3, which is what? So like 3.31 kilonewtons. So all what we are trying to say is that if I use 9.93, then it means that technically speaking, I have multiplied 3.31 by 3. That's basically what it means. Okay, so thank you very much for watching.